Up until now with electrochemistry, we've been discussing basically a chemical reaction turning into an chemical energy. Let's just look. What have we been doing? We have had chemical energy via a reaction, products going to, or reactants going to product. Chemical energy has given us electrical. One day I'll learn to spell, huh? Giving us electrical energy. Essentially, we've been looking at a battery, haven't we? That's what we've been doing. Now, what we're going to do now is we're going to talk electrochemistry again, but we're now going to be talking about electrolytic cells. All right, we are going to do electrical energy and we are going to use it in chemicals. Okay, so we are going to use this to produce that. In the past, we used this to produce that. The difference here is we are going to be using electricity. I stress. Therefore, guys, when you see a problem and it's got a battery in it, I know I sound like I'm being facetious, but it's a trigger. When you see a battery connected to a pot of stuff, it's an electrolytic cell. We are putting a current in there. Let us start, okay? I'm going to start a page or so in on mine because then I'm going to go back to the question that is posed. Let us take, for example, a solution over here. Right, I am just going to put in over here, and I'm going to take a solution over here of NaCl. So I am going to put NaCl solid, and I'm going to put it into plus H2O, and we know we're going to get Na plus Cl minus. That process is we get ions formed. So what have I got in this water? We have got Na plus and we've got Cl minus. Correct? Cool. We have also got in here H2O as a liquid. Okay? Don't ionize that yet. Okay? Just leave it. Okay? So we've got water sitting in there as well. Now, along we come, and now we're going to put our battery into there. Well, first of all, we're going to connect it up like so, and there we go. This is our EMF over there. It's a battery. So I say that's plus and that is minus, okay? According to my battery, not a problem. So go with the logic here. There's the battery. I'm using the battery indicator to tell me which side is which, okay? If I do that, it means that the positive side, all right? What is going to be over here is pluses, and this is going to be minuses, is it not? Correct? Therefore, what do I say? I then look and I say, right, in the water here, the chlorine is minus, so it is going to migrate, okay, to the positive. And the Na, and I'll do that one in red, the Na is going to go to the negative, migrate to the negative. Okay, I think we're all pretty clear on that, all right? So in this situation, we have got that, where the ions are migrating and they are at the same time, they are surrounded by water. Okay, so there's water around each one of those. Now we ask ourselves, all right then, what actually could happen? Well, we could have the sodium at this side. Let me do it under each one. So we say over here, I could have the Na plus, not plus 2, the Na plus, okay, gaining an electron, going to Na metal, solid. The opposite side, okay, I could have the Cl minus changing to Cl2 gas, right, plus 2 electrons. Now I identify this one over here is I've got my, we're migrating there, so the sodium there would be keeping it, it's going to go, this is gain, we've got reduction over here. This side I'm losing, so this must be oxidation, correct? Can you see what I'm doing? I haven't labeled my electrodes yet, okay? I haven't done that. So I've said it's oxidation. Oxidation, the next step means it must be the anode, right? So I can now go up and I can label you. I can say you are the anode and you are the cathode, right? So I've got the anode and I've got the cathode, okay? And we're all very, very happy about that. So therefore, what we've got is we've got the oxidation side, okay, is the anode, and the other one is the cathode. Right? So the chlorine is, let me balance it, sorry, my bad, I didn't in my sort of thing. That's a 2Cl and a 2 electrons, okay? And the sodium is balanced. So anything that we put in here is going to be affected by the electric current. My question to you is, do you think that we could get this forming at the anode over here? Could sodium as a metal form in water? If anybody says yes, gee, then you obviously didn't see that experiment way back when we were young, where we put a block of sodium on water. It doesn't coexist very well. It runs around on the top forming hydrogen gas. Remember? Sodium and water, lithium and water, and generally all of those metals, okay, lithium, sodium, potassium, rubidium, cesium, okay, we're not going to put those in water, but essentially they're all going to yield a hydrogen gas, correct? Yeah. Potassium more reactive than sodium. Potassium, if you put enough, it goes boom. Okay, you get quite a big bang out of it. Now, and a flame as well. It's pretty cool. Look up on the YouTube or whichever one you want to use. Have a look at what happens when you put it. It's worth doing because it gives you a good grounding for this. Now, what are we saying? We're saying, okay, cool. Therefore, I've got, can you see I've gone through the logic? But now, so what is going to happen? What else can happen? This is where we start now looking at the possibility of, let's just say we've got water as well. What if we just did this? Once again, we can go back to an experiment that was possibly not done a long time ago, all right? But it's definitely in the textbooks, well, the ones I've seen anyway. So we say plus and a minus, and all we're going to do is we've got pure water in here as a liquid. Do you remember that what we did is we had a little apparatus that we had a thingy over here which basically caught the gases coming off, and we piped the gases that way, and we piped the gases that way, we collected them, and then we looked at what they were. Essentially what happened is that the water itself was electrolyzed. The water changed to hydrogen gas and oxygen gas. Now let me just stop at that point. The theories are that originally on the planet we had hydrogen gas and we had O2 gas, and water was formed via an electrical discharge, lightning, okay, and apparently we had some serious storms in those days to create H2O. I haven't balanced it, I'm aware of that. So you're going to have 2 and 2, and you're going to have 2 hydrogens, and you're going to have 2 waters 2 O's, 4, that's correct. So what we can say here is that this reaction can occur over here. They are equilibrium reactions. So water itself, we put a drop of acid in there, if you remember, in the experiment. That was to get the current going, right? So we found that water itself was actually split up into the hydrogen and the oxygen component. Let's have a look at water. All right. Now, we've got the equations over here. And if you look, I'm going to put them down over here now. So what happens, this side is going to be plus. This side is going to be minus. Okay. So now let's have a look at how do we find, what are we saying? We're asking water to turn into, let's take the top one, hydrogen gas. This is what we've got. This is our reactant. This is our product. Remember? This is our reactant. These are our products over here. So we need a balanced equation that looks like that. So we're asking water to turn to hydrogen. Okay. How do we do that? Now, if you go and look at your half reactions, you will find this equation, 2H2O plus 2E minus going to H2 plus 2OH minus. This was a gas, the water, the electrons, 2OH minus, and you will find it at minus 0.83 volts. What am I saying? It's kind of in the top part. Remember, I work lithium down to fluorine. Standardize on one table, whichever your educator prefers. Use that. I'm working down. The voltages are going to be fine. So I'm saying minus 0.83 volts. Just recapping that, minus 0.83 is relative to the standard hydrogen electrode, remember? So we've got that situation. Now, this one over here then is this is reduction, isn't it? Okay, gaining electrons. So this is our reduction. Reduction is happening here. Okay, gaining electrodes. So then it must be the cathode. All right. So the reduction is happening there. So let's find the opposite one. The opposite one must be 2H2O going to O2 gas plus 4H plus 4 electrons. That is at plus 1 point, is at plus 1.23 volts. Okay, stop me at this point and find those two. If you got them. Now, if you've got them, what I recommend to students is when you start this section, find these two here as step one. All right, find them. Find them on the half reaction table. And draw a pencil line under them so that you've got the one and the other one, because they are actually the outer limits of water's actual electrolysis. I'll explain when I get there, but it's important that you find those two and draw a pencil line underneath them. It's a good place to start with the electrolysis electrolytic cells. Our situation is thus that we are saying that this is possible, right? So this is possible. Now you can see here, this is water going to oxygen. Now I would obviously have to balance it. You'd have to multiply by 2, etc. to get the final reaction. Then our electrons would cancel out and you will get a final reaction, basically the water going to hydrogen and oxygen, which is the top reaction over here. Okay, multiply that by 2 and then just add them. The electrons cancel out, and basically that and that are going to become water as well, leaving us with hydrogen and oxygen, which is a gas there. So if you look now, you've got a line at the top and you've got a line at the bottom, close to the top and close to the bottom. Right? Now we're going to refer back to that line. Okay, we're going to refer back to that line. I am going to use it now, in fact. Okay, back to our original example with sodium and chlorine. Put the reduction reaction of water. Remember, you've now got a line through it. I'm going to redo it. 2H2O plus 2 electrons, okay, going to H2O gas plus 2OH minus, like so. Now this is at minus 0.83. You've got it already as a line. Now I'm going to label above. All right? I'm going to label above and I'm going to label below. I take the reduction, I label above and below. Reduction, it's the one on the half reaction chart. It's the one that's showing which way it's going, correct? It's written in reduction potentials. So we've got that. Above. Above, they stay. Below, they go. They stay in solution. They go out of solution. Which means if I look at it, let's have a look. So let me take this down just a bit. All right. Have a look. What is above? Okay. If you have a look, you will see that above it is you've got, well, let me just take out my table again. Use this one because it's handy. Okay. So I've got it drawn in there at minus 0.83. You can see what is above it over here is chromium plus 2, Mn plus 2, aluminium, magnesium, sodium, potassium. So all of those are above. They will stay in solution. You won't get them out. What will come out is Zn, chromium. Okay, that's a chromium. Fe. All right. Cadmium, nickel cadmium batteries, nickel, tin, lead, nickel, tin, lead. These will come out because they are underneath. Have a look at that. Stop this and go and look at it and say, right, there's my line. The ones above, heck, you know, potassium isn't going to come out as a solid in water. It doesn't happen. What it means is that the water starts to break down first. Okay? So what happens is over here, if you get there, the water will break down and we get, look what Kevin's written here. Not H2O gas, Kevin, it's H2. Sorry, please just correct, it's hydrogen gas there. We get H2 gas. So can you see the water has broken down? Because the stuff above it, it's not going to come out of solution. It gets to that point and then the water says no more. And once again, we start getting hydrogen coming off, right? So that's our upper limit. Okay, this is the upper limit. The next step is to say, okay, then now let's go and have a look at the lower limit, shall we? Let's have a look at the lower limit, all right? On the other side, we've got H2O. We've got this one, let me just write it down, 2H2O, liquid. And you can see here plus is going to go to O2 plus 4H plus 4 electrons. This is now our oxidation anode. Anode side, okay? And I mean, you can go and see what's happening at the anode there. So, and we'll go back up to it and put it in. So this is the oxidation is at the anode. So what is going to happen here is on this side, we are going to get, around here, we're going to get oxygen. Now, basically, generally, nonmetals are produced at the anode. Let's take this down. Generally, nonmetals are produced at the anode. Right? But But, big but. Chlorine, bromine, yep, and what do you think the other one is? You're right. Iodine will be produced. Okay, but chlorine, bromine, iodine produced. It always freaks me when it does that. Will be produced in preference to O2. So if there are halides, therefore the halogens will be liberated before O2, but not fluorine, not F2 gas. No, it's too far down. All right. And also O2 will be liberated. O2 will be liberated before NO3 minus and SO4 minus, okay, which are other anions. Okay. Therefore, we are saying that in this process we now look at in each and every one where there is water. Some of them we're going to get to don't have water in them. We don't look at the water because it's not there. We only look at the ions we have actually in solution. In those we're going to melt, things like bauxite and so on. All right, we're going to get to those. Now, in a thing we're going to look at copper chloride in solution. There's a few standard ones which are looked at, and copper chloride is looked at. But the first step is we always say, right, what have we got? Now, let's have a look here. Let's have a look at hydrolysis of copper chloride. Oh, let me go back. Sorry, I haven't finished. All right. We said at the anode we get oxygen. All right. So at the anode we get oxygen. So what is happening over here? All right. We're going to get at the anode, we're going to get the oxidation. We're going to get the oxygen coming out, aren't we? So the next now step is to say, righty ho. Let's have a look at copper chloride in solution. Okay. What do we have? We have got our pot. All right. And inside here we've got CuCl, which means we've got Cu plus 2 and Cl minus ions wandering around. CuCl, please note, it goes from a solid to Cu plus 2 plus 2Cl. It is 1 mole to 1 mole plus 2 moles. Very important that we recognize that. The next step is we're now going to put our electrodes into this little mixture, and we're going to connect them up to a battery like that. We say plus and we say minus. Now you go and you say, all right, don't forget we've got H2O in here as well. So what can happen? We can have the copper ions, okay? The plus ones are going to migrate there, and the chlorine ions, the red ones, are going to go that way. Because they're minus, they're going to be attracted to plus. So what can happen? All right. What are our options? Let's look at what the options are. What are the options? All right. Over here, all right, on this side here, I can have, let's look first there. It's always easier to look at the metal first. Copper plus 2 electrons could come out as copper solid, correct? What's happening? Gain, this is reduction, which means it must be the cathode, correct? Therefore, on the other side, we've got Cl minus is going, what can happen to Cl minus? It can only turn to Cl gas. That's all we're bothering about with this. And that's going to give off 2 electrons. And I think it's going to have a 2 over there like so. This is loss of electrons. This is then going to be my oxidation, which means it's the anode. So the chlorine side is going to be the anode, all right, and the other side is going to be the cathode. All right. So now we've labeled them. So the copper's gone to the cathode and the anode. Now please, I haven't mentioned it, but it is the reverse of the galvanic. But don't stress. All you're going to do is you're doing it from first principles. You have to remember that. I don't sit here saying, oh, it's opposite. I just say it's connected to a battery, and I look what's going to happen with a typical copper ion or a zinc or anything I'm given. So therefore our options are that. But now remember, we've also got the option, all right, on this side of H2O going to O2 gas plus 4H plus, because we've drawn our thingy. Okay, this is the other option we've got. And the other option on the cathode side, on the cathode side, is we've got the hydrogen. We've got the other option over here. I just want to write it here. I'll write it above. We've got 2H2O. All right. This is the options. The 2H2O plus 2 electrons could also change to H2 gas plus 2OH minus. That's the water breaking down. So how do we decide? We then say, okay, well, that's what we've got in solution. Now, how do I make a decision? Look at the top limit first, remember? Okay, look at the top limit and say, right, the top one is water. There it is. Start over here. Okay, start there, because that's our top one. The water, that's minus 0.83, correct? Minus 0.83 volts there. Let me just check myself. Minus 0.83 volts, that one. So we start there and we say, all right then, I'm now going to have a look. I'm going to start there, 2H2O plus 2 electrons going to the H2 gas. This is my upper limit, okay, plus 2OH minus. Then I say above, stay. Below, go. All right? Easy to remember. And I look and see, now look and see which, not which, look and see where is the metal they're talking about. Look and see where the metal is we are looking at. Copper, plus 2 electrons going to Cu solid, and you will see that in fact that is, now I've got to find it, it's way down at 0.34. Okay, it is below. Therefore, copper will go out of, below is go, out of solution. Right? Straightforward. The next step is to look at the lower limit. Lower limit. Okay? The lower limit was our water breaking to oxygen. 2H2O going to O2 plus 4H minus plus 4 electrons. And now I compare. What's my equation I'm looking at? I'm looking at 2Cl minus. It's either, which one of those two is going to happen here? Well, you already know because we've discussed it. O2 gas, Cl2 gas, plus 2 electrons. Okay. What's going to happen? This one. Why? It's a halide, will produce a halogen. Let me redo that. Otherwise my editor gets all upset. Becomes a halogen, doesn't it? The halide becomes a halogen. It's a chlorine, iodine, or a bromine. They're going to come out. Okay. They're going to come out of the solution. So generally we find oxygen coming out unless we've got a halogen in there. Now in this case we've got a halide 2Cl minus, so we're going to get chlorine gas. So if I go up, I'm going to get chlorine gas coming off the one side. Let me go to the red side over here. The red side over here, I'm going to get Cl2 gas. And on the other side, I'm going to get, let me just go back to green, I'm going to get copper solid coming out over there. And that's all we do. Just go through the logic. Okay, we're going to do more. I've got a whole pile of them here we're going to do. And we're going to do some plating as well. All right, I'll be back. But remember, in the meantime, the recipe says, look what's in your pot. Look at the ions that have been formed in the pot. Zinc, chlorides, sulfates, nitrates, whatever they are. Then label it and say which is the positive and the negative, and look which ions are going to go which way. Then write down the reactions, the reduction, the oxidation reactions. Then we look and see, at the top one, we write our upper limit for water, and we look above, it's going to stay in solution. So hydrogen will come out. Below, they are going to precipitate out. You go to the lower, if there's halides in there, in other words, iodine, bromine, chlorine, they will come out. Otherwise, generally, it's going to be oxygen. Okay? Right, and remember, all of this is very concentration dependent. Very concentration dependent. Let's make a note of that. This is depending on concentration. So when you're going through this, we're going to do another one now. Please just follow that recipe. Write it down. Put your upper limit in pencil, put your lower limit, and go through the one I've done, and you'll see, bang, it works. Cheers. Have a good one. Be back and we'll carry on with these. Bye.